This is session 19 for models in epidemiology and biostatistics. I am Gordon Hilton Fick. And for session 19, we're going to start with the challenging topic of hidden extrapolation, and then we'll talk about the inappropriate use of explanatory variables. Then later in the session, we're going to look at models that use a link other than the logit link. We're going to be looking at models for binary response variables, health outcomes, that use either the log link or the identity link. And some of this material is actually quite new. So we'll start this session then with a consideration of the circumstances in which one should not be using certain explanatory variables to address either modification or confounding or, frankly, any use within a model. And this may be somewhat counterintuitive. You might be thinking, what harm can it do to at least explore an explanatory variable that may be associated with the health outcome in some way? So let me begin by describing a particular circumstance in which we have extrapolation that is not wanted, so-called hidden extrapolation. To do this, I thought it was appropriate to give you an example. We'll keep it anonymized. We'll have an outcome that's dichotomous, an exposure that is dichotomous, and we'll have a person's age. And you might be thinking, okay, well, that sounds quite fine. Let's just have a look then at the implications of a model that uses age or does not use age. So although we would normally start an assessment with, say, addressing whether or not age is a modifier, and then perhaps confounder, and then perhaps even a crude analysis, but let's kind of do it in a reverse way. And I think it'll be clear what I'm attempting as we move forward here. So let's suppose we have then the following 2x2 table. And one can see here that there is an apparent strong association with the health outcome and exposure. Indeed, an odds ratio estimate of much greater than 9, even the lower limit of the confidence interval well above 4. Okay. And then we get the comparable crude analysis with logistic regression, and that number 2.2416 is just the logarithm of 9.4 here. And so you might be thinking, okay, well, that's quite interesting here. We have then that there does appear to be an outcome exposure relationship. And there are the details. Pretty substantial. But then you might be thinking, well, what about an analysis that assesses modification and then potentially confounding? What are the implications? So let's now rethink the use of age first as a modifier. And if we do that, we get an indication of a relationship between the exposure outcome relationship and its dependency on age. And you can see that we're getting a number that is fairly large, although perhaps not statistically significant. What is of interest here, though, is to have a look, and what I strongly encourage all of you to do is not just stop with the if I may, the analytical stuff, but look at a visual. So here's a graph then of the results that we get from such a logistic regression. And what we'll see is that, let me show you, oh, right. The slopes are quite different. All right. And here, what I have done is graphed the exposed, that is this line, that is the set of fitted values on the log odds scale, and then the unexposed. Okay, you might be thinking, okay, at least visually we're seeing what appears to be an indication of that age is a modifier, although perhaps not statistically significant here. Let's just proceed with the supposition that we're interested in exploring this modification. Well, what are the implications here? Well, it means we can explore for any specific age, we can explore the estimate of the difference between the two log odds. So, for example, for a 50-year-old person here, we would be looking at the exposed and the non-exposed. And for a 10-year-old person here, we've got the exposed and the non-exposed, and you can see they're different. But you may well have now noticed that what I'm doing here is the red line and the blue line refer to actual predictions on the log odds scale. And these dotted lines, this orange line here and this green line here, are extrapolations of these lines in order to make age-specific estimates of the difference in log odds or the log odds ratio. So what do we see here? For the 50-year-olds, we're seeing a difference, quite substantial, one that's actual, but one for which we have no one. This green dotted line is an extension of the blue line where there is no one. So this is an anticipation that such a relationship between the log odds of this outcome for the unexposed can be extended to individuals that are much older. Notice here we're seeing that the unexposed, the oldest person that was unexposed was about 35. Same thing here. For the exposed, the youngest person was about 30. All this orange line here is an extension of the actual predictions that we get from the logistic regression. And what do we see here? That sure, for a 10-year-old, we could imagine an estimate of the log odds ratio that's given by this minus this point here on this dotted line and this point on the blue line. And again, the construction of that age-specific log odds ratio estimate involves an extrapolation of the red line to individuals for which there was no one. There was nobody. Among the exposed individuals in this study, no one was younger than 35. We don't know whether or not such a set of predictions, if you like, or estimates for given sets of individuals would be extendable. Now, what that means is that we are making an assumption without data that this linearity extends into ranges for which there was no one. There's a larger issue here, too. This study is exploring a disease, or in this case, outcome exposure relationship, but it would seem that really age and exposure are very closely related. Knowing a person's age, and knowing, for example, that a person's age was under 35, or under 30, say, means we know that person was not exposed. And similarly, for a person that was, say, over 35 here, and within this range, it means we knew they were exposed. Okay. So there's a lot going on in this picture that we did not get from the stata analysis of just the estimates of the regression coefficients and standard errors and so on. Okay. So here is an explanation in words. Now, it is also true that we can see there was almost no overlap in the age distributions. The exposed and the unexposed were almost distinguished by their ages. Just going back to that picture again, you can see that it's only for this narrower range of ages, from roughly, say, 30 to 35, that we have anybody that we could construct an age-specific estimate of the log odds ratio here. This number here in the red minus this number here in the blue. And you can see that that's viable perhaps, but again, maybe only based on a small number of individuals. Okay, so what is it? What's in play here then? Well, let me elaborate a little bit here. It is fairly standard within the epidemiologic community that if one is contemplating a particular explanatory variable as a confounder, that one would like to know that in fact the characteristic, say age here, has the potential to confound if the distribution of ages for those who are exposed is different from the distribution of ages for those who are not exposed. And that is certainly true. On the other hand, we can see that if there is essentially no overlap in those age distributions, that we have a dilemma, and that is that the use of a model to assess the impact of age, and we'll look at the confounding issue in a minute, but the modification issue here is really fantasy. It's really not real. So what we can see is that I've drawn the lines for 10-year-olds and 50-year-olds. So maybe, if I may, I'll just emphasize that when one is contemplating the consideration of, say, age here as a confounder, in the literature you'll see people will report for example, the average age among those exposed and the average age among those not exposed. And if those averages are different, then sometimes authors will say, well, then we have the potential for age as a confounder. And as I said, that could be true. But maybe what's even more crucial here isn't just the reporting of an age or an average age for the two groups, but something more crucial, and that is, okay, not only are the distributions different, but they do meaningfully overlap, though, that we do have individuals in both exposed and unexposed for most ages, and that the implicit comparisons, age-specific comparisons we would make to assess modification here are real. They're not phony in any sense. Okay. So let's look at this from the point of view of a situation in which we maybe made the decision that age was not a modifier. And so we proceed with the model again that removes the term that is the product of age and exposure. And when you do that, and then here's the stata code for constructing the two lines again, this is what we see. We see two lines that are parallel now. Yes, we know that. And we have an assumed common difference between the two parallel lines, and that is the estimate of the, if I may, the adjusted log odds ratio in this instance. However, we have exactly the same issue, maybe a little less obviously displayed here, but we have exactly the same issue as we did from the model that was enabling us to address modification. And that is, except for a tiny range of ages, from age 30 to 35 roughly, the assumed common difference is actually a difference between an actual and an imaginary or an extrapolated value, to be I guess a little more fair. Same thing here, that among the young people we can see that the assumed common difference is actually, for example, for the 10-year-olds, a comparison between a number that is based on an extrapolation and an actual set of predictions that are available from the model. So the difference here, the assumed common difference that we speak of somewhat, in a comfortable way most of the time. Yes, assumed common. We know what that means. It's common to all ages. Yes, that's true. However, well, it really is only applicable for a comparatively narrow range unless we are prepared to assume that the extrapolation of the red line for those under age 30 and the extrapolation of the blue line for those over age 35 is at all meaningful. So notice here that it is the fact that the average ages for the exposed and unexposed are certainly different here. That's quite clear from this display. But the maybe more troubling issue is that the overlap in those two age distributions is very small. So there's the estimate of the assumed common difference. However, that extrapolation is in play. Whether or not it is at all reasonable to suppose such an extrapolation of those two lines into ranges of individuals that we did not have. Now, I think it's worth keeping in mind here that what's going on is the fact that exposure and age are very closely related here. The age distribution tells us a lot about whether or not a person is exposed or unexposed. So I think it should then be clear that unless you're really able somehow to make the assumption that this extrapolation and the assumption of linearity into ranges of individuals we did not have and maybe could not have. That is the other possibility here, that maybe it's just not possible to have young people that are exposed. Maybe it's just not possible to have older people that are not exposed. It just doesn't happen. Okay. Also, a reminder that the analysis that Stata gives with the p-values and estimates of the logarithm of the odds ratio of the odds ratios here gives us no hint that there's trouble. So in this particular investigation, there were 250 unexposed persons in the study and 250 exposed. But it turned out that, in fact, the oldest unexposed person was only 33, and the youngest exposed person was 28. So there were only 11 unexposed in the overlap, and 14 exposed in the overlap amongst all the individuals in the study. Are we prepared, although the study was based on 500 people, to use an analysis that really, at its most generous, would be applicable to only 25 individuals? Troubling, right? Let's take a look at a second example that may give us a cue to a different matter. We can see here, for example, that with this data set, there is apparently, with a crude analysis, no indication of a disease, of an outcome exposure relationship. Okay, fair enough. And what we get is a small but perhaps meaningful estimate of the difference between the two log odds ratios for that is involving age, for this age characteristic. And I would encourage you, if you haven't done this for a while, to write out this model and provide interpretations for these regression coefficients. And here again, we might say, well, there's apparently no evidence of modification. What does the visual look like in this instance? Well, you could do so. But if we then proceeded with another analysis that perhaps decided against modification, and then exploring the issue of the impact of the outcome exposure relationship adjusted for age, well, we get something interesting here. Notice now we're getting a big outcome exposure relationship with adjustment for age, whereas with the crude we did not. Okay. Well, you might be thinking, oh, this adjustment then really seems to be important here. Let's look then at the graph of the two sets of fitted values we would get from this particular model. Okay. And here's what the two lines look like. The red line for those who are exposed, and the blue line for those who are not exposed. And you might be thinking, okay, well, if I was to draw a vertical line between the red line and the blue line, I would see quite a large difference. And that's what we're seeing. That assumed common difference would be, for example, for say a 30-year-old here, this point on the red line minus this point on the blue line. And so what we're getting is a quite large, if I may, adjusted estimate of the log odds ratio here. But maybe it's not quite so obvious. But again, the range of overlap is quite narrow. The youngest person here, about 30, amongst the exposed, and amongst the unexposed, the oldest person, about, again, a bit more than 30. Okay? It's not as completely obvious. Let's look at the visual when we extend the lines like we did in the previous example. Okay, so, and I'm referring to the extension to Fantasyland where there was no one. And if you do so this is the same graph, but what I'm doing now is extending the red line, that for the exposed, into the younger ages, and I'm extending the blue line into the older people, the blue line for the unexposed here. And again, what we see is a quite narrow range for which the actual analysis applies. In other words, we can construct then the assumed common difference between these two lines, but for a comparatively narrow range of individuals for which we have actual persons. Most of these assumed common differences here, for example, again, for the 10-year-olds and for the 50-year-olds, involve a comparison between actual fitted values and extrapolated fitted values for which we have no one. So what's different in this instance with this example is the crude suggested no relationship, but the adjusted suggested quite a strong relationship. The adjusted, though, involves the very demanding assumption of linearity for both the exposed and unexposed into ranges for which there is no one. Are we comfortable with that type of assumption? And again, what we're really dealing with is that the age relationship with exposure is very tight. Knowing a person's age tells you a lot about whether they were exposed or not, and vice versa. Okay? So again, the real issue here is we can see if in fact we were wondering about age as a potential confounder here, we can see that the average age for the exposed is quite different from the average age from the unexposed, right? However, there's very little overlap in these ages, and hence the challenge of hidden extrapolation. Okay. So what we've seen is empirically where one might be tempted to adjust for something that we would like to refer to as a confounder, but really we should not. In both cases, both my example 1 and example 2, what we're really faced with is just the crude analysis and not the model that gave us an assessment of modification, and not the model that was enabling us to assess confounding. Those models are fantasy because of this hidden extrapolation issue. Now, sometimes in real investigations with your own data, you should probably spend a little bit of time exploring your contemplated or the variables you're considering as candidates for the explanatory variables for the right-hand side of a regression analysis. And the challenge that I think is that one needs to look at the distribution of that particular characteristic, okay, and look at the overlaps. It's not often, sadly, it's not often something that is considered necessary. But boy, oh boy, there's probably more than a few circumstances in which investigations were done blithely using characteristics that are supposedly enabling us to construct an adjusted odds ratio, in which the adjustment involves explanatory variables for which there is this hidden extrapolation issue. This is a tough one, quite tough. Well, I have a couple more examples to comment on fairly briefly of ones for which I have had discussions with colleagues over the years and relating to this particular issue. The first one involves some of my colleagues who are involved in ICU investigations. And I think that this particular circumstance will give you an indication of a particular instance in which it would be very clear that one should be careful about using an explanatory variable in a model to address issues of confounding, modification, or otherwise. And this comes from the fact that we might well have measurements that are taken throughout the course of a person's stay in the ICU. And we might well have then interest in determining which of these, for example, might be associated with the 30-day survival outcome in this particular case. But what is widely identified as a very, very troubling circumstance is in investigations in which these measures that are taken just before a person is no longer in the ICU, either because they passed away or because they were discharged. And if one considers such a measurement that's associated with maybe a current status of their health, if we include such measures taken just before a person leaves the ICU, then it is widely known that such models with either adjustment or, in fact, that characteristic specific consideration with modification will actually remove the ability to see anything that's relevant. And such a characteristic would then swamp or dominate the distinction between maybe the interventions that are really crucial. So it's widely known then that for ICU researchers that one should not consider adjustment for measurements that are taken late in a person's stay in ICU. It is widely identified that characteristics measured at entry into the ICU, their baseline characteristics, are typically suitable for assessment in a model, say, for assessing modification or confounding, but not the later measurements, right? Now, again, we'd anticipate that these late measurements are just going to be ruled out as potential explanatory variables. And the issue isn't so much because of the empirical judgments that we looked at earlier, but rather the common sense implications here. That we have to consider the merits of when a particular explanatory variable can be used. Now, I have one more matter to show you, and that is that there are also instances in which specialists in a particular field, frankly, to my knowledge at least, do not agree as to whether or not one should be using such a variable. So I thought I would end this part of this session with one example, again from a circumstance that I have been consulted with concerning a particular issue. Now, again, I'm only just going to mention this quite briefly at this point. This comes from the Sloan Epidemiology Unit birth defect study. Here the outcome, a neural tube defect, and the exposure, and essentially wondering whether or not supplementation with folic acid is a benefit to avoiding neural tube defects in newborn children. So what is the challenging part here? Well, there is also available to the investigator a variable that details whether or not the child, all these children died, but did they die as a result of the birth being a stillbirth, or was there in fact an induced abortion? Pretty tough stuff here. So we have then an outcome, the presence, absence of a neural tube defect, the exposure, the supplementation with folic acid, and the potential variable to be considered as a confounder or modifier, or just added to the analysis, is the variable that is an indicator for stillbirth or, in fact, induced abortion. And here is a small example of this. The odds ratios then for those in the two groups, this is the induced abortion, and these are the stillbirths, and they're different, but not statistically meaningfully so. You can see that we are getting quite wide confidence limits here. Oops. I'm skipping a lot of the crucial details. But what do we see then if we make the decision here to not consider this characteristic of whether it's stillbirth or induced abortion? We're ruling out modification now, and now looking at confounding. And here is what became somewhat of a challenge for the investigators. The crude and the adjusted estimates are different. Maybe you might not say hugely so, but for example, the confidence limits one gets for the crude do not include the null, but for the adjusted, the confidence limits do include the null. Slightly higher, slightly closer to the null when one adjusts for this stillbirth induced abortion variable. And when one does not, one gets an indication of a relationship, right? That perhaps supplementation with folic acid is reducing the neurotube defect outcome. And so the dilemma is, should we be adjusting for this variable C or not? And that is, I believe this is true, that experts in this area are still not entirely sure whether or not it is appropriate or meaningful to adjust for C here. And there's a lot that's been written about this, and I guess I won't try to attempt anything definitive here, except to point out that the dilemma associated with the possibly incorrect use of explanatory variables is oftentimes a non-trivial topic. It's not just about, oh, well, let's put it in the model and take it out. It's really about, should I be considering such a characteristic in an analysis or not? Now, again, I can see that, well, one might argue that this quantity C is known after both the exposure and the outcome, but this isn't quite clear either. For example, it might be that there were plans for an induced abortion, and that the relationship, or between the temporal relationship here of whether it's the child died, say, by stillbirth, presumably naturally, I guess, or whether or not it was the result of an induced abortion. Pretty tough stuff. Anyhow, the literature on this topic then provides many different commentaries about this. And that's all I'm going to say on that. And now we're going to move on to a section for this particular session on the log link and the identity link used in epidemiology these days. All right, let's now consider two models that have only been briefly mentioned in earlier sessions, and I wanted to give you some of the details here now and some of the current news about the use of links other than the logit link. Now, what we know is that if we use the logit link, or the log of the odds, we get logistic regression. An area of considerable interest and ongoing and involving myself and some of my colleagues has been the study of the logarithmic link And some of you may know these models as log binomial models, or sometimes just binomial regression with a log link. So notice on the left-hand side now, instead of having the log of the odds, we have the log of the probability. And then we have the usual set of the explanatory variables on the right-hand side. All right, we can now repeat what this might look like for a couple of quite simple log binomial models. Let's take a look, for example, at the crude. We might then have that the log of the probability of disease, say, is given by this particular model. And like we did in an earlier session in this series, we can specialize this model to both the unexposed and the exposed. And if we do so, we can see that when E is 0, we get that the log of the probability for the unexposed is beta naught. Further, when E is 1, we get the log of the probability for the exposed is beta naught plus beta 1. And so we can then see, following in the same pattern that we've used previously with logistic regression, that beta 1 here is then the difference between the log of the probability for those exposed and the log of the probability for those unexposed. And that turns out to be the log of the ratio of those two probabilities. And hence the exponent of beta 1 is what we would call the probability ratio. Or if indeed we have put the negative characteristic here, that is disease, is the probability that's under study here, then we would see this probability ratio as a risk ratio, or sometimes even relative risk. And as I mentioned in an earlier session, we could spin this as a health ratio, by the way. Instead of having the probability of disease, we would have the probability of the absence of disease. And that leads to something that is not the same as the risk ratio. The health ratio and the risk ratio are not the same. And we've discussed that earlier, but now we're looking at it from the point of view of the two distinct log binomial models. Okay, let's now briefly look at what we would have had earlier. Consider the model then, very much like we saw in an earlier session, that enables us to determine whether or not the strata characteristic here with two levels, s equals 0 and s equals 1, is potentially modifying. But now modification with regard to the log link, not the logit. And so what do we see? Proceeding with the specialization of this model as we did before, we can see that beta 1 is the log of the ratio of probabilities for those in strata 0. And beta 1 plus beta 3 is the log of the ratio of probabilities for those in strata 1. Aha! We can see we get two risk ratios. We get the risk ratio for those in strata 0, and we get the risk ratio for those in strata 1. And so we can see that we get essentially the same implications that we saw with logistic regression. Instead of it being statements about odds ratios now, we're making statements about the logarithms of probability ratios. Odds ratios are being replaced. Odds ratios being replaced with probability ratios, or the more elaborate things as we've discussed. And just going back here quite quickly, we can see that the difference between beta 3 plus beta 1 and beta 1 is beta 3. And what is that? It's the difference between the two stratum-specific log risk ratios. And that is telling us about whether or not the strata modifies. But here it is the modification of the probability ratio, or the two risk ratios in this instance. So notice, and I hope this is quite clear, for almost all circumstances, modification will be specific to the measure of association. In other words, we've seen this in earlier examples, not with the models, but just with the tables, that modification can be specific to the measure of association, or we can see can be specific to the link used. The comparison between the logit link and the log link analysis may yield different things. For example, we might well see that with the logit link, we see modification, but with the log link, we do not. And I would also remind you here again that not only is there the log probability, but there's all the log of 1 minus the probability, giving us health ratios rather than risk ratios, and that those things are different. So it could be that the health ratio analysis is different from the risk ratio analysis, and it's different from the odds ratio analysis. Right. There's 3 different links really here involved. And the identification of modification depends on the link. Same thing with the identification of confounding. The identification of confounding depends on the link. It's fairly well known that modification assessment is dependent on the link. Maybe not nearly as well noted in the literature that modification is also a function of the link. Okay. So what we can do is go back to the very beginning of all these sessions and return our attention to the Callflesh data. And here are the 2 analyses of this being labeled as the risk ratio estimates, and although the label here is, this is the health ratio, because it's success rate here. So these are health ratio estimates, and here are risk ratio estimates. And I won't repeat all this, but the modification is very definitely present with the risk ratio analysis, but not present with the health ratio analysis. And there's quite a bit that you could revisit here if you wanted to consider this analysis again. Might be a good time to go back to session 1 and have a look at all of the material that I hope you all feel some sense of comfort with now. And we can recover the analysis here using the risk ratio option in Stata and the command called binreg for binomial regression. Saying RR here and specifying coefficients is giving us estimates of log odds ratios and the estimate of the ratio of the 2 odds ratio estimates here. Right. And we've covered this before. So notice that with this analysis, that is the health ratio analysis, we see no indication of modification. And so we might then proceed. Whereas with the risk ratio analysis, we do. This number here, very definitely non-zero. And the p-value very small. Okay, so that's recovering then the logistic regression, the log binomial regression in terms of failure, and the log binomial regression in terms of success. And they're different. And again, it's not surprising that the regression analyses, the log binomial regression analyses, are different, because the so-called classic analysis with the 2x2 tables reveals that as well. And the two analyses are essentially the same. Okay. And so we could then, for example, here then is the analysis of success without the term for modification here. And this is, again, enabling us to reproduce what we would have seen if we had carried out the analysis on the log binomial scale. This is the in this case the health ratio analysis, right? The success here is the health ratio analysis. And just to remind you again, with the health ratio analysis, we saw no indication of modification, but with the risk ratio analysis, we did. And so, and we have the two binomial regressions in terms of the both health ratio and the risk ratio, essentially duplicating. And similarly, the analysis for which we remove the term that's addressing modification here and get the then adjusted estimate that, again, would be the same or essentially the same as one sees from the classical analysis. So BinReg is successful here in giving us analyses. The data set here, the Call-Flush data set, is successful with this particular analysis. But I wanted to now show you an example for which this particular log binomial regression is not successful. This particular illustration comes from my colleague, Dr. Misha Ilyashu, and we've devoted, Misha and I, along with individuals who were at one time students and are now colleagues, have been dealing with this particular example on and off because of the fact that the analysis that one gets from Stata using BinReg, as we're going to see in a minute, goes wrong. So here is what looks like perfectly okay regression coefficient estimates. This is an additive model. We have an outcome, which we'll call disease, and 3 potential exposures. And the investigators here were considering an additive model. And what we see is, sure, strong indication of a relationship with each. And these are estimates assumed common to the. So this number here is an estimate of the presence compared with the absence of exposure 1, assumed common to exposures 2 and 3. And I would trust that you could carry out that part of the analysis. However, now we come to the trouble. It turns out that with log binomial regression, the fitted values must be negative. Okay, they must be negative. Why? Because the logarithm of a probability is a number that is less than 0. So the estimates we get have to be such that the fitted values we get for all possible configurations of the exposure variables here are negative. We can't have a log probability estimate that is greater than 0, because that would yield to a probability estimate that's greater than 1, which is nonsense. Well, what happens if I construct, the fitted values with this particular quite notorious example? Well, all of the predictions or all of the fitted values are negative, but one of them isn't. One of them is very definitely not. It is 0.5, which is much greater than 0. Hence, the exponent, which is the supposed probability estimate, is above 1, which is obviously, and you can see here I've annotated this, that's clearly wrong. What we're dealing here with this particular model, the log binomial model, is what are called the constraints on the parameter space. There are certain restrictions that must be in play here. So we began a quite extended exploration of this particular data set. And it became clear when we explored what was happening here, this number here that is not negative, applying to the individual, the only one, but the one individual for which all three of the exposure variables were present. And that led to an indication that the boundary to the parameter space, this is a bit on the technical side, I guess, but that in fact, in order to ensure that the fitted values are negative or 0, there were a bunch of boundaries, but the crucial boundary in play was that the sum of the regression coefficients had to be 0. Well, after some quite extended exploration of the log likelihood function, it became clear that the maximum likelihood estimate was either very close to this boundary or maybe even on this boundary. Okay, tough issues. A maximum likelihood estimate that's very close to a boundary. It turns out that many of the classic issues for maximum likelihood fall down whenever the MLE is either very close to a boundary or even on a boundary. And so the actual use of this particular model requires a lot more care than just the standard approaches that investigators have used. So what did we do? Well, we then realized that, well, if the MLE were on the boundary, then that would mean that we actually really only have 3 regression coefficients. And one way to re-parameterize things is to just identify that if beta naught is, again, if the sum of the coefficients is 0, then beta naught is the negative of the sum of the other 3. And that leads us to a model that looks like this. Okay, so there's no constant term, and each of the exposure variables has been adjusted to give us that the use of this characteristic. Well, if you do that, well, guess what? We can specify in stata no constant, so we get a fit that does not involve the there is no beta naught in this particular analysis. And, well, it turns out we get a quite viable set of regression coefficient estimates. We still have to view it as tentative because, well, are these values real or not? I mean, they came from the assumption that the regression coefficients that the maximum likelihood estimate here is actually on a boundary. And so you could say, well, is this real or not? Well, just quite quickly here, one can then explore the 8 different fitted values, and indeed we do get an exactly 0 in this particular circumstance. And these are now the means in each case here. Okay. I think I have that now correct for you now. Yes, I believe so. All right. Here are the one. Oh, no, sorry. I'm fumbling on this a little bit. This isn't just the fitted values from the second fit. This is the corrected one, but the incorrect ones that we got from the phony fit gave us this one fitted value, which is clearly wrong. And what I'll draw to your attention is that this fit that uses the assumption that the MLE is on the boundary gives us 0 for that one cell. And what is also of interest here is to notice that all the other fitted values are quite different. So not only was the initial model that we used giving us the wrong fitted values for that one particular characteristic, that one particular combination of explanatory variables here, where we got an estimate that wasn't negative, but all the other values are wrong too. Again, this is somewhat tentative in that we're basing it on the assumption that that the MLE is actually right on the boundary. Okay. So this is what one gets if one attempts to use the model binreg here, but we're using it in such a way that we give Stata's algorithm a chance by giving them starting values that assume that the MLE was on the boundary, and when we then refit, we get numbers that are actually quite close to the. Now we're going to look at another type of binomial regression. This is binomial regression with what is usually referred to as identity link. In other words, there is essentially no function. There's no log odds, there's no log probability. It's just the identity, the probability. Identity binomial regression models, or binomial regression with the identity link. Okay, let's take a look at this particular model exactly as we have already done. And what do we have? Well, we can think of now the probability of those with disease given exposure and the probability of disease given the absence of exposure. A crude model, and what do we see? Following the process of specializing this model to the unexposed and the exposed, we see that beta naught is now, in fact, the risk difference. Aha! Widely considered. Sometimes these models are called risk difference models, in that we have then the ability to estimate risk differences or health differences, perhaps. And if I reverse code. But in this particular case, the identity link gives only one distinct analysis, like logistic regression. And unlike the log link, which gives us 2 different analyses, one for the essentially functions of the probability of disease, and another quite distinct model that's based on the probability of the absence of disease, and giving us things like risk ratios and or health ratios. But with the identity link, there is only one model, essentially. So the crude model gives us the risk difference directly. And like we did previously with the logit link and with the log link, we can then consider a model that includes the ability to assess whether or not strata here are modifying the two risk differences. And what do we see? In this particular case, the risk difference in strata 0 is beta naught, and the risk difference in strata 1 is beta 1 plus beta 3, and hence the difference between the two risk differences is beta 3. So again, we see that beta 3 enables us to assess whether or not the stratum characteristic here modifies the risk differences. Does the risk difference depend on the strata? Notice there's no logarithms here. There's no exponentials. There's a certain simplicity here, isn't there? There's not too much going on. So with risk difference regression or binomial regression with the identity link, we have interpretations directly, no logarithms, and we get rate differences instead of odds ratios or rate ratios, and functions of rate differences, like a difference between rate differences, and so on. So what do we find in this particular analysis using the risk difference? Now in BinReg, we use the option RD for risk difference. And if we were to return to the Callflesh data, we get exactly the analyses we saw for the circumstance in which we're considering the possibility of a surgery type as a modifier or not. And it doesn't depend on whether we study the outcome as a failure or the outcome as a success. The only thing that changes is the sign, and everything else is the same. Unfortunately, when one attempts to use the analysis, this BinReg analysis tool in Stata, unless you give Stata very good starting values, the algorithm does not converge. Now, I'm showing you here an analysis for which we did give pretty sound starting values, and this was after a lot of identification here. So the point being here is that back in the day, when there were not options for the analysis of models using the binomial regression with the identity link, there were times in which you had to be very, very careful about whether or not you were getting the right analyses or not. But now I'd like to take a few minutes and show you some quite current material that is quite specific to R. To my knowledge, at least, these algorithms that I'm going to show you next are only available with R, although it could well be that again, that might be changing, and maybe people who are interested in this and with Stata might be able to do a more detailed search here. Okay, now let's take a look at some comparatively recent analyses using R. And the libraries that one needs to use are BLM for binomial identity link, and we have LBReg for the log binomial regression. And here I'm going to show you then a bit of the Stata code that one be needed. So the packages need to be installed are BLM and LBReg. And here I'm then showing you a little bit of the analyses that we considered using Stata and BinReg. So I'll begin with the use of R's GLM with the default family, and the analysis here of this is the logistic regression, and you could compare this with the results that we've displayed earlier. This is the additive model that is the challenging one with the column flush data, not with logistic regression, but with the logit link and the log link, and with the identity link. And what is of interest to see here is that LB-reg, without needing any fancy starting values, gives the correct estimates of the regression coefficients for the log link. And if you use BLM, then you get the correct estimates without any need to give stata, or excuse me, are the fancy initial starting values. The algorithms are quite good now. So LB-reg for the log link, for the log binomial model, and BLM for the identity link, or the identity binomial model. And it's, again, this is comparatively recent, and there's quite a bit that you could read here. Certainly, though, if one is considering a log binomial model, then the tool LB-reg now is very, very thoroughly studied and gives very reliable results. Same thing with BLM and the identity link model, or the identity binomial model. This was very hard to get. These regression coefficients, quite hard to get in the world of Stata and BinReg, but frankly rather effortless with R's packages BLM and LB-reg. Okay, and I thought you might be interested in the same thing with the data set that was provided by my colleague, Dr. Ilyashu, Misha. And if one uses LB-reg here with that rather notorious analysis that we spent a fair bit of time with, right? We engaged in that analysis quite a bit. And what was in play here? Well, we needed to consider the possibility that the MLE was at or near a boundary, coming up with starting values that were near the boundary or on the boundary, and then refitting. Well, with LB-reg, we get exactly the right numbers. And that looks to be an extremely stable state of affairs here. So, again, if one is using the log link and with a dichotomous outcome, with a binary health outcome, LB-reg looks to be very, very good. Similarly, just for interest's sake here, I'm showing you the identity link analysis, or the identity binomial regression analyses from that particular data set. And you can compare that with BinReg.